So let me just kick off with a question. The question is, why does the universe extend as far as the moon? That might seem like a bit of a ridiculous question, but in my opinion, the absurdity of it is not in the question, but in our current understanding and our current interpretation of our preferred models of particle physics and our preferred model of gravity. Because basically, as you well know, if I just take the electron and I calculate its 0-point energy, so Pauli was the first to point this out, I calculate the 0-point energy of the electron and I work out to what extent does that curve the universe, then the cosmological horizon wouldn't even extend as far as the moon. So we know that there's not just the electron, there's a whole bunch of other particles as well, and their 0-point energy is enough to curve the universe by a huge amount. And that's clearly not what's happening. And this is, of course, the essence of the cosmological constant problem. Now, there's various approaches that you might take to tackle the cosmological constant problem. You could appeal to quantum gravity. I don't think that really fits with the notion of decoupling. I think I should be able to solve the cosmological constant problem in the realms of effective field theory without worrying quite what the UV completion is. I mean, it's certainly true that the standard model itself, the standard model particles themselves, are already enough to give you a problem. And we've already talked about the electron and how much that wants to curve the universe. So I think this is already a low energy problem. We don't need to appeal to quantum gravity to try and solve it. We shouldn't have to. You might hope there's some sort of symmetry. You might resort to anthropic principles, whatever. Okay?
Do we know that 0-point is relevant?
Well, we think it should, because we believe in equivalence principle and we believe in general covariance. But I'm actually going to show you a way to stop it from gravitating, is the point of this talk. Okay? So, naively you would say yes, in general relativity, yes. But, that's the opening gambit of my talk, but let me come to that. Okay, so there is a view you could take, which is kind of related to Kirill's question, is particle physics hasn't done a very good job of trying to address the question of the 0-point energy of all the standard model particles. So you could take a different view. You could say, well, I'm just going to accept that the 0-point energy is large, but I'm going to phrase the question differently. I'm going to ask not why the vacuum energy is small, but why it hardly gravitates. That's how I'm going to phrase the question. So I'm going to try and stop it from gravitating. I'm going to try and stop that 0-point energy of the electron from affecting the curvature of the universe. Now, Weinberg famously came up with a no-go theorem that says, well, you can't really do that. Okay? I mean, you could imagine, say, I have a huge vacuum energy, and then I have general relativity plus some additional fields, whatever spin, it doesn't really matter. Weinberg's theorem is very general. I have some additional fields in the game, and whatever their job is to absorb that big vacuum energy and protect the, your metric, your physical metric, from getting curved, okay, by that vacuum energy. Now, Weinberg has a theorem that says you can't do these kind of self-adjustment mechanisms. And it's a very general theorem. Now, what Nemanja and I did while Nemanja was visiting last year was we found a very nice way around that theorem. And what I really like about what we did is that we cut straight to the core of the cosmological constant problem in the following way. Suppose you want to try and eat up vacuum energy in the way that sort of Weinberg was talking about, for example. Well, if you're going to do that, you've got to know that the thing that you're trying to eat up is indeed a vacuum energy. Okay? And to know that the thing you're trying to eat up is truly a vacuum energy, you have to scan the whole of space and the whole of time. Because otherwise you have no way of distinguishing what you're talking about from a vacuum energy, which is truly constant over space and time, or say a potential which is just temporarily flat. Maybe it's flat for a certain amount of time, or it's flat in this room, but far outside the room it's going to decay off into some different value. If I truly want to zoom in on the cosmological constant and the vacuum energy, then I have to scan the whole of space and time. So this is truly a global question. If you want to eat that guy up, you've got to address the cosmological constant on a global level. This was emphasized by Nima, Kani Hamed, Savas Dimopoulos, Dvali, Gabadadze, famously. And what I like about what we've done is that we find a way to do that. We find a way to modify gravity, but on a global level, such as to attack the cosmological constant problem, at least at the level of the standard model. We say nothing about graviton loops. And because we're attacking gravity, we're changing gravity just at a global level, we don't get any problems with local physics. Locally, the theory just looks like GR. Okay. So, we don't have to jump through hoops with screening mechanisms and all this kind of palaver. We don't have to do any of that because we're actually modifying gravity globally. But that's all you need to do to address this question. So let me... Yeah, that's local. Yeah, because you're locally fixing the... since Kirill's brought up unimodular gravity, let's explain why unimodular gravity... Okay, so firstly, it's clearly a local. It's because what you're doing is you're fixing the metric determinant to be constant. It's a local statement. It's also a sort of, in a sense, an empty statement because it's just a gauge fixing. Okay, so it is indeed true that, as Hippocrates and I are going to write a paper about this shortly, but the unimodular gravity is GR. I mean, you can see it even. So it's very easy to see just classically. So for those that don't know it, unimodular gravity, you take the action for GR, but you vary it under the restriction that the metric determinant is fixed. And it turns out the equations of motion you get out are the following. It's basically the traceless Einstein equations. Okay. Now, what you now do is you just say, okay, I'll take the divergence of this equation, and I've got the Bianchi identity, and you get a constraint which I think is something like this. Might have a sign wrong there, it's not important. And then, and so from that, you integrate that up once, and you get an integration constant, which is lambda. And when you feed that back into the equation, you end up with g mu nu is t mu nu minus lambda g mu nu. So you might say, oh, well, that's an integration constant now, but the problem still persists because what you really, as I'll explain, you can only fix that integration constant once. Okay? Just as you, and that's no different from only being able to fix that parameter, the bare cosmological constant in the GR action once. It's the same. So there's no difference. So this clearly doesn't solve the cosmological constant problem. If you want to think of it, I'm loath to say this with Kirill in the audience, but if you want to think of this at the level of path integrals, then it's kind of obvious that they have to be the same thing. Because, if you think of the path integral for, okay, I'm going to write this, which Kirill will get upset by. Okay, so however I'll define it perturbatively, shall we say. Okay, and I have my action for GR. Okay, so this is for GR. Now, I divide the path integral like that, I should divide out by the diffs. Okay, if it's unimodular, I should divide out by t diffs. And in the end, I end up with the same thing. How's that not true? Of course it's true. No, but I'm dividing out by all the... It's an integral, but maybe we can discuss this. It'd be interesting, particularly with Hippocrates, it'd be interesting to discuss any subtleties there. But at least naively, it's just a gauge fixing. That's what I want to emphasize.
I'm also under the impression that the action, there's not, the action formalism of what you're writing there, there is more than one. It's not only one where you just keep the metric fixed. This is where they name it emotional game, but there are people that propose other action principles of these equations. And the basic properties at the end that you get equations which are trace-free, essentially. So
yeah, well, either way, it's still, I can perform this operation and it's trivially the same. But also, I think even then, it's still just a gauge fixing. So, one gauge, if I fix the metric determinant, that is a gauge-dependent statement. Okay, there's one way that can be made very clear, and that's if I add a Stuckelberg field. Okay, and I can introduce the constraint that that even at level of path integral, that's okay. So if I take GR and I add oh, this is going into something completely different actually, but I can have a Stuckelberg theorem which I can then integrate out, and it becomes the same theory. It's kind of trivial, but at least classically, it's trivially the same. I think quantum mechanically, it's also the same.
That's where the statement is a bit tricky, because classically it's trivially the same, but the point is the way you define the theory affects the quantum mechanical behavior.
Yeah, sure. Okay, fine.
Vacuum energy with gravity.
Fine. And this is now becoming a seminar on what Hippocrates and I talk to be thick. But yes.
I mean, before when you were talking about when Kirill asked if vacuum energy gravitates, Tassos was too shy to ask, so he pushed me to ask, essentially, to say that essentially the vacuum energy problem, I mean, the magnitude of the cosmological constant is a flat space quantum field theory. Okay?
Oh, right, yeah, sure.
So it's very crucial how you will go from there to quantum gravity. I mean, you said that quantum gravity...
No, decoupling. No. That's not the same thing. That's not the same statement. So I would say that I should be able to work with an effective field theory. I should be able to work with effective field. If I believe in effective field theory, then I can take GR plus the standard model, and I can work with that. And then I can do that, and then I can do my calculations in that picture. And assuming I agree that you have to be a little bit careful about calculating these vacuum energy contributions in curved space, blah 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 blah. Okay.
Vacuum energy is not just large. It's actually really normal.
Sure.
All the subject is how.
But the key issue is how how it runs, and that these mass to the 4 terms keep coming in as you're moving your cutoff.
So that's an effective semi-classical theory, right? I mean, you're taking this...
Yes, I'm working with effective field theory. And if I believe that in decoupling, which I do, then I should not expect. I should be able to. Low energy physics should be insensitive to the details of the high energy completion. Otherwise, I wiggle something here, and what goes on far away? I mean, come on.
Yeah, go ahead.
Okay. But I really don't buy the quantum gravity can solve this. I think we already have a problem with our effective field theory, unless we abandon effective field theory, which I don't think we have to do. Okay, so I'm going to show you. Okay, so let me now. That's taken. Okay. Okay, so let me talk a little bit about what I mean by the cosmological constant problem. And then we'll go on to describe this proposal. Okay, so cosmological constant problem, what is it? We've already discussed it a bit. But basically, I think you've got two important ingredients in general relativity. You've got general covariance, and you've got the equivalence principle. And these basically tell you that the vacuum energy should gravitate. Okay, and they tell you how it should gravitate. Typically in QFT, the vacuum energy comes in as a constant, like so. General covariance said I have a covariant measure, so stick a root G in there. And now I vary this with respect to G, and it gives me a contribution to the energy momentum tensor. This is all pretty non-controversial stuff, I hope, and I get that. But that's okay, that's not the full story, because you can always add a bare lambda. Okay, so you add a lambda bare. And then really what's gravitating is now the combination. So lambda total is the combination of VVAC and lambda bare. Okay? So this is the guy that's gravitating. And then you say...
Now you're thinking of some calculation with some loop.
Yes, let me come to that. Let me come to that in a minute. So at least, so we have this overall combined thing, this lambda total, and this doesn't dilute with the expansion of the universe, like sort of all the other anything that satisfies the standard energy conditions. So, given that it didn't dominate in the past, I could get a bound that this should not exceed the critical density, which is 1 millielectron volts a fourth. Okay. So then you go, okay, well, what's the natural value of VVAC? And you say, oh, maybe it's up at a TeV, blah, blah, blah. Oh, that means I need to fine-tune. I'm coming, just shush for a second. I'm coming to all of that. I'm going through the standard arguments, and then I'm going to say specifically what I really think the problem is. Okay. Okay, so people will say, oh, you've got to fine-tune lambda bear to, all these decimal places, 60 decimal places, whatever it is, okay, to get this cancellation. Yes, fine. That's not really the problem, though. Fine-tuning is okay. You do fine-tuning all the time in quantum field theory. In fact, you calculate the charge of the electron, you get an infinite contribution, you cancel it off. It's renormalization, okay? So what's really the problem? The problem is that the thing you're trying to fine-tune is not radiatively stable. That is the problem, okay? Now, there's various ways you can think about radiative stability. I'm going to express it in the language of perturbative QFT. You don't have to do that. You can talk about proper ways, really, in terms of Wilsonian effective actions, but I like describing it in terms of successive loops. I like this sort of way to describe it. So what's the issue of radiative stability? Okay, radiative instability, in fact, here. So I'm going to express this in the language of perturbative QFT. Okay. So I want to calculate VVAC. Okay, I'm talking about perturbative QFT. You tell me how many loops. Okay, do it to one loop. That's the issue. So calculate VVAC to one loop. One loop. Fine, let's do it. So you calculate it, you've got your matter fields, and you get your tree level contribution, and you get your one loop correction. And typically, what you find is that you get contributions from every particle up to the cutoff, and each particle will give its mass to the fourth, typically. So this, well, typically, one way of doing it is you just take, okay, I can do I have one loop, so I have some matter field, Klein-Gordon field or something. I'm just going to do. You can do it at the level of Wilsonian effect, but here I'm just doing it in the language of loops, corrections, higher order loops. I am calculating. I don't need to do that because I've got general covariance. All I need to do is calculate that diagram. A single H. Yes. And I know by general covariance it's going to come in as a root G. Yes. If you like. And I can calculate that diagram, and then it gives me, and I know it's going to enter as a root G. I do as an expansion about flat space. So I've got an interaction which tells me how the H interacts with the. I can do this calculation. I did an example of this calculation in our longer draft, which isn't out yet. But you can do more sophisticated things with effective actions and all that. But you can also do, and then then you calculate the one loop correction. You might do something like this, sorts of things. That's kind of the thing you would do. But anyway, bottom line is you always get mass to the fourth. It's just a dimension. Dim reg. Okay, let me use dim reg. In the calculation I did in our paper, it's dim reg. Yes, but each particle gives its mass to the fourth. So if this particle had mass m, it would be contributing mass to the fourth. Okay? And there's some logarithmic running, obviously. And a divergent piece, which throw away. What I'm going to emphasize is, what each particle contributes mass to the fourth, so that sort of tells you in a way how to this guy. Yeah. It goes something like, I'm trying to remember now. I think it goes something, if I calculate these guys, I get a divergent piece, which, if it's dim reg, I think I get something like that, and then I get log of, There's numerical factors which I'm not sure what they are. This would be your RG scale.
So what should be calculated? If it's that, then it has the right dimension.
Yes. No. What I'm okay. So I see. Yes. So right. Okay. I can take my action. So I take GR coupled to let's say a massive scalar field. I expand it about flat space. I expand all my so there's a e to mu nu plus h, and I write down. I know what all the interactions are, and so I can now calculate this guy because I know what this vertex is. And then there's factors. If I canonically normalize that, the h, then there may be factors of M Planck, powers of M Planck coming in here. But in the end, when everything comes out in the wash, I mean, V back has dimension 4. You know that. Well, you do know that, right? It's an energy density. Well, do we really want to? I mean, this is not controversial. This is standard, okay? And the factors of M Planck are just, you can take care of them straightforwardly. The only other thing that can come in here are factors of M Planck, because you know the scale in the game at this stage. Yes, but there might even be, yeah, it depends how I'm normalizing these guys and whatnot, but in the end...
So M is the mass of the scalar field, remember that?
Yes.
So why is this
Sorry, why is...
this formula a problem?
This formula is not a problem at this stage. It's just the formula. Okay. So let me just say, generally, each particle, all the way up to your cutoff, contributes its mass to the fourth. Okay. So I'm typically going to get cutoff to the fourth here. Why are you following us? It's not controversial. I take particles all the way up to the cutoff. They each contribute their mass to the fourth. Assuming there's particles up near the cutoff, this is that.
So you assume that there is a particle whose mass.
Yes. This is okay. If you want to say this is the heaviest particle underneath the cutoff. Okay. Take this at TV.
It's also divergent. So
Well, I'm neglecting the divergent piece. I'm neglecting the divergent piece. That's true. I'm doing some, subtraction scheme to. Yes, of course. Yes, you could do this calculation. Yes, I agree. Of course it does. It tells you that it runs with all the mass terms kicking in. It doesn't just. There's not some simple running. It's running like fourth powers. Maybe like steps because it's really mass terms coming in. But yes. But I can do it in the language of dim-reg, and I like the language of dim-reg because it picks out. Really tells you that it's the particles themselves that are in the spectrum that are causing the issues. Okay, so now, this cutoff, well, we can take the standard model up to the TV, more or less. Okay, so this is of order at least, you expect this to be at least a TV to 4, really. Give or take a factor or 2. What really matters is the differences, actually, which is the next step. And then I think the differences are going to correct themselves. And that's what I emphasize. This is what I think is the important point. This is what the really important point is the differences, the changes. When I go to 2 loops now, so anyway, so I get this huge number, and then this is the standard element, and I would naively say, okay, I now have to choose lambda bet, 60 decimal places, blah, blah, blah. Fine. Okay. The problem now, so you fine-tune lambda bet. The problem now is you go to 2 loops. And you repeat the calculation. You do it. And what you find is, because this coupling generically here is not massively suppressed, this is typically more or less, maybe given a few factors, but of order MUV to the 4th as well. This guy, sorry, I should say this, VVAC 2 loops is of order more or less, maybe there might be a factor of 10 out or 100 out, but certainly not enough to eat up 60 decimal places. Is more or less of order the 1 loop calculation. Similar order.
It's so strange to me because Planck mass is somewhere in this calculation, and tools are different. Planck mass.
The Planck mass, yes, so, okay. Right. Planck mass, do your expansion of your graviton. Okay, canonically normalized. Planck mass now appears in the coupling, so it now appears in this coupling strength here. Yeah, I think it might be school. Yes, it's a single power. Yes, it's because it's a single H. Correct. Right.
This guy appeared, not gravity.
Yes. So then when I put everything back in, it's yes. Okay, I didn't realize that was the point. Yes, these are scale. Yes, these are, and that's a very important point. I'm doing matter loops here. Yes. What I'm going to say has nothing to say about graviton loops. Good point. Okay. Anyway, so now this contribution is pretty much the same order, which means I have to, the value I chose at one loop for this lambda bear is now rubbish. I now need to retune it to the same degree of precision. Okay? So that's not good. And then you go to 3 loops, and you need to retune again to the same degree of precision. Not for a radiatively stable quantity. If you forget the divergent pieces, if you focus on the finite pieces, then it's certainly true that if you've got a radiatively stable quantity like electron charge, then you only have to fine-tune the Baire values once, and that's a stable fine-tuning. The Higgs mass, on the other hand, does not. Then again you have the problem that you need to keep retuning order by order in perturbation theory, and that's radiative stability. If you prefer, I think you will prefer, you can think of Wilsonian effective actions, and what I'm saying now is I define my effective action with some cutoff, and I integrate all the high energy modes. I get some vacuum energy contribution. I choose my low energy Baire parameter to cancel it off to whatever degree of precision. Now I move the cutoff, and I recalculate. And now that low energy parameter I chose needs to be rechosen. That's radiative instability, if you prefer it in that language. But this, I like the loop language. But that's how you can think of it in observativity, in that sense. Anyway, the point I wanted to make is it's not really a question of one-off fine-tuning that's the problem. It's the fact that you repeatedly have to fine-tune this low energy parameter, lambda Baire. That's the real problem. Okay. And as I said, it's already a problem, the level within low energy theory. It's already a problem with the standard model. I don't need to quantum gravity, schmontum gravity, but I don't need to worry about it. This is already a problem with classical GR plus standard model. Okay, so as I said, you might hope to get some sort of modification of GR, which some extra fields adjust themselves and eat up this large vacuum energy contribution. That doesn't work, typically because of Weinberg's theorem. Well, yeah, Weinberg's theorem is very restrictive, at least in that respect. So what I'm going to propose is something which gets around that problem in a I like to think, a very minimal way. And it's quite radical, but also it's not very radical because it does very little violence to general relativity. Okay, so let me write down the action. Okay, so I'll write down the action, and then I'll hope you'll recognize this action. Okay, now, obviously this isn't quite the action, because I guess most people are going to recognize that guy. What is this action? Just general relativity coupled to some matter sector, where these matter fields psi are minimally coupled to the metric. That's GR. Clearly, that doesn't solve the cosmological constant problem in any way. Okay? So what am I going to do to this to try and improve the situation? Well, first thing I want to do is I have this parameter lambda, right, which is the bare cosmological constant. I'm now going to promote this to a variable. Now, I don't mean that it varies over space-time. I do not mean that it's constant in space-time. What I'm saying is I'm altering the variational principle so that I'm allowing myself to vary over this global parameter. Okay? So, if I just stopped now and did that, what would I get? I would get a constraint that the space-time volume was 0, which is clearly nonsense, right? So I'm not going to stop there, but the very first statement is that I'm going to vary over this guy. But it still remains constant in space-time. I'm just altering the variational principle. The second thing I want to do is I need to know about the matter sector, because it's the matter sector that give me all these annoying fourth powers of the masses that are causing me the problems. So what I'm going to do is I'm going to introduce another parameter, which again is going to be global. Okay. Little lambda. Okay, so this is global. Again, this does not vary in space-time. Okay, it's constant in space-time, but I'm going to allow myself to vary at the level of variational principle. Okay, and what does this little lambda do? This little lambda essentially sets the hierarchy between the mass scales in the matter sector and the Planck mass. So for example, to see that, you can look at this piece of the action here. So the matter action enters like so. Okay? Now this is entirely equivalent to the following. Okay, where G tilde is just some constant multiple of the other metric. Okay, so all lambda's doing is rescaling the metric. So because of that, if I have some, if you like, some bare mass parameter in here or in here, so let me call that M, and I want to extract the physical mass, then it turns out that that's just lambda times it. It's just setting the scales. Okay, so really, if you like, lambda sets the hierarchy between the physical masses and the Planck mass. So in particular, if lambda went to 0, that would send all the physical masses to 0, even if the bare parameters went 0. Okay, so that's what little lambda does. It knows something about scale, if you like, in the matter sector. And in particular also, the other thing I want to emphasize is by different variance, there's different variance here, and so when I consider loop corrections, they're all going to scale with lambda the same way because of different variance. Matter loop corrections. Okay, fine. So this is not quite the full story. So there's my two global variables. I'm going to add one extra ingredient, and that's the following. I'm going to add to the action something like this. So what I'm going to do is I'm going to arrange it so that big lambda and little lambda talk to one another. Okay, so I have to add some interaction. This is the interaction I'm going to add. This is not integrated. This is not covered by the integral. The integral does not cover this term. These are global, right? So then they're not included in the integral. And in fact, actually, I can make this a general function of that, and it doesn't alter things. Okay? Big lambda over little lambda to the fourth, and then there's mu to the fourth, which is just a mass scale that's just introduced for dimensional reasons. So it's just a mass scale. It can be Planckian depending on the choice of sigma, and in the end, if you want these to match, dimension of lambda is dimensionless. Which lambda? Big lambda, little. Dimension 4. Yeah, I haven't got the m Plancks in it. Yeah, it's dimension 4 here. So that's why it's mu to the fourth. And little lambda's dimensionless. Okay, so that's not. There's just details. But anyway, the point is, I'm going to take this guy, allow it to vary, not in space-time, but at the level of the action. I've got this thing that knows about scale. I'm going to allow that to vary, and allow the two to talk to each other. Okay, and I've chosen a particular way for how they talk to each other. That's certainly true. Now, I'm not going to treat the graviton quantum mechanically, and nor am I going to treat the global guys as quantum mechanical either. They're all being treated classically. What the quantum mechanical corrections are, I do not know, and that's another story. Okay, that'll be something very interesting to explore. Okay, but what I'm going to treat quantum mechanically is the matter sector. Okay, but that's all I need to do. I'm working at a level of effective field theory. Okay, so I have these global guys. Okay, so what are the equations of motion now I get from this? Well, let's see. Okay, so from big lambda's variation, I get sigma primed of lambda to the 4 mu to the 4th. So sigma prime, this is just, well, it is sigma prime, is equal to the space-time volume. Okay? Hopefully that's not too difficult to see. Little lambda equation of motion. This is a little bit more tricky, but it's not too hard to show that you get the following. Right, and T tilde here is it's what I would get from varying the matter action if I neglected the little lambdas, essentially, in a way. Okay, so I just running out of space there. But it's basically what you get if you just neglect the little lambdas. Okay, and if the lambda to the 4 comes in, that's expected. It's just dimensional grounds. T is dimension 4 guy. So you expect that because of this result, you can see that a lambda to the 4 might come in, and indeed it does. And then finally you have the G equation of motion, which is of course the only local equation. And this gives you the following. Okay, so the first thing I want to do is I just want to identify this whole thing with T. Let me just call that T mu nu from now on, like the physical energy momentum tensor. I'm absorbing the lambda in there. So, what's different to GR here? Well, this obviously last equation looks very GR-like, and of course it is, because locally, this is the local equation, and we haven't changed any of the local physics. What's different is we now have something which tells us what this is. Which is not true in GR. There's nothing which constrains it. Now, the global equations of motion do constrain it. In fact, these two equations, when you combine them, it tells you that big lambda, these two equations, tells you that big lambda is a quarter the space-time average of T alpha alpha, where the space-time average of a quantity Q is, hopefully, does what it says on the tin, it's the space-time average. Okay. So this is what those equations tell you. Okay, the 4 comes in on dimensional grounds. Fine. So I now know what the classical the bare cosmological constant is. The dynamics are telling me it. So what does this mean? So it means if I plug it back into that last local equation, I get T mu nu minus a quarter space-time average of T delta mu nu. Fine. So now you look at this T and you split it up. You split it up into vacuum energy and then excitations about the vacuum. And that vacuum energy you can calculate to any order in loops that you like. It's not going to change the story. Okay? And I plug it back into the equation. Well, the first thing I've got to do is I've got to calculate this guy. So I take the trace. That's easy enough. And now I take the space-time average. Well, the space-time average of a constant is just the same constant, obviously. This takes the average. and I plug it back in, and hopefully you can see that this factor, miracle of the factor of 4, you're now going to get a cancellation. VVAC is going to drop out entirely. And all you're left with is the following. It just sees the excitations. Standard model vacuum energy is dropped out completely. At any order in loops. Doesn't matter how I calculate it, it's gone. Now,
You get the same answer if I take GR action.
Yep.
Vary with respect to total volume. Well, vary with respect to almost, well, just do arbitrary variation of the measure, but keeping total volume fixed. You want to get that.
is that, I think that's probably true.
Like range multiplier.
I think that's it, that you will, yes. That corresponds to a special case, I think, where sigma is linear. I think. Yes, I think that's true.
So it's 1% equal to
Yes, I think that's fair. So in a sense, I think Savas, when Nemanja gave his talk in Stanford, I think Savas made a similar point where he said that in a sense what you've got here is you've got solution by legislation, which I think is fair. But the point is that my response to that when Nemanja told me that he said that was that yes, but these laws work generation after generation after generation after generation. You know, the law that worked in the 16th century works in the 17th century and the 18th century and so on. So by that I mean they're in successive loops. It doesn't matter, you know, at what order I calculate VVAC, it will still cancel. And actually, so this whole thing was inspired by a model of Saitlin, where what he did was he just took the GR action and divided it by the space-time volume. And you get something quite similar, but and so you can see then that obviously the root G, integral of root G is cancelled, but it multiplies the cosmological constant term, and so you might think that you're solving the problem then. Now in his case, he does, of course, cancel off the classical contributions to cosmological constant, but the loops don't come in with the right behavior, and actually the loops screw him. Okay. He also has a problem with the Planck mass getting too large renormalizations, which we don't have a problem with. But yeah, so yes, I think that's fair. It is, if you like, solution by legislation, but it's a law which transcends generations. Is what I was saying. Anyway, so this is what you've got left. It's not. There are no hidden equations like unimodular gravity. There's none of this business. Take the divergence of this. Everything goes. This is just a constant, remember. So this is divergence free, so no issue there. There is, of course, I haven't killed vacuum energy, well, I haven't killed, let's say, vacuum curvature entirely. In the following sense, there is a cosmological constant there. There is a residual cosmological constant, which is this. Okay? So we call that lambda effective. But the point about this is totally independent of the vacuum energy. This just knows about the excitations. Okay. This is a radiatively stable quantity as well.
So let's go back and redo your Tuckball picture.
Well, those diagrams don't even contribute to this equation. Those vacuum diagrams do not contribute to this equation, so, because they all enter like in VVAC. And VVAC only. So I'm only interested in local excitations of these guys. I guess these guys are the guys that I guess we've got external, probably got external matter legs. Okay. So then the question is, so this is good, we've cancelled the back energy, but the story's not complete. Now we have to worry about how big this is. And this is where there's some weak anthropics come in. Okay. We have dealt with the standard model contributions of fact. That is gone. Has it gone consistently? If I then took this and I applied these equations to our universe and I found out that I got some huge lambda effective, then that would clearly be inconsistent. Okay? So I can now tell you that you get a small lambda effective. Let's estimate how big it is. Before I cancel VVAC, all vacuum energy contributions gone. But there is this residual leftover piece. It essentially it corresponds to the fact that if you look at this action, if you forget the M-Planck piece, there's a global symmetry. M-Planck breaks it slightly, and I think this corresponds to this leftover piece. This is where you get this leftover. It's like a global scale invariance. Well, it's kind of a fake scale invariance in a sense. I mean, you take, I can't remember what it is off the top of my head. It's something like, you rescale G, you rescale little lambda, just to keep that combination invariant, and then you do some rescaling of big lambda in a similar way, and it stays invariant. Also, there's a shift symmetry in that as well. If you shift the Lagrangian by a constant, then there's some complicated readjustment, field redefinition of the other terms that can absorb that. So this is why the cancellation happens. There is a certain level of symmetry, but the scale invariance is broken by M-Planck, and I think that's what contributes to this. That's why you get this leftover piece. Anyway, so the question is, how big is this guy? Right? This has got nothing to do with vacuum energy. This is relatively stable quantity. This is all about the physical excitations of the universe. This is the standard model vacuum energy has gone, which is what we're set out to do. Okay, so how big is this leftover contribution? Well, there's something I haven't said. Now, let's just imagine for simplicity, and it generalizes, imagine for simplicity that sigma is linear. Okay? So sigma prime is just a constant. And this is easy to see now. Can I have infinite space-time? Infinite volume space-time. So this guy's infinite. Well, you'd see mu is just a mass scale, right? So that would correspond to lambda going to 0. Okay? But if lambda goes to 0, my physical masses are going to 0 relative to Planck mass. Okay? That's not our universe. So I immediately infer from this that I cannot have infinite space-time. Okay? Now, there are generalizations that we've since thought of which don't demand that, but in the original manifestation of the theory that this is true. This can only have finite space-time volume. Okay. Because otherwise the Planck, it just can't possibly correspond to our universe. So that means the universe should have finite spatial size, perhaps a lot bigger than the horizon, but whatever. And it should be a band crunch universe. Okay? Fine. So that has certain observational consequences. For example, dark energy wouldn't be able to be a true cosmological constant in that scenario, because otherwise it would just expand the universe forever. So it would have to be some transient state, so perhaps there's some quintessence or something like that. Anyway, the point I want to make is that, so let's accept for the moment that space-time volume is finite, and let's try and estimate this. It turns out that these integrals, when you calculate, it's not obvious immediately, but when you calculate them, you throw in some standard matter fluids, satisfying standard energy conditions, and all these matter fluids, I mean, they're everything except for, basically the equation state goes between -1 and 1, not including -1 because it's not vacuum energy. And what you find is that these integrals are dominated by the point at which the universe is at its largest. Okay. So, for example, if I were to estimate what the space-time volume is, it turns out that this typically goes like 1 over h to the 4th, where the age of the universe, so the typical timescale of the universe is 1 over hh. So this is t age, if you like, is the age of the universe at which it starts to turn round. So this would be bigger than the age of the universe today. Okay, so this is some time in the future. Because as I said, these integrals get dominated by the point at which the universe is its largest size. If you compute this guy, it turns out, similar reason, it just gets dominated by its value at its largest size. These aren't obvious statements, but you can show it. And this is given roughly by rho age, where rho age is the energy density of the matter fluid at the point that the universe turns around. Okay? And so this is, of course, less than the critical density now. So what this is telling us is that this residual cosmological constant is definitely no bigger than the critical density today. So this is not dark energy. This is not dark energy, this guy. In fact, it's very small. It's small. It's smaller than the dark energy scale. So we're left with the residual cosmological constant, but it's small. Okay, so I'm... Yes, but the matter fluids aren't necessarily zero density. So this, if I say took a closed universe and matter, for the sake of argument, then this would be the energy density of the matter. I see what you mean. Yes. Yes. It's TH. That's why, it's just the scale of the turnarounds, the universe at turnaround, the characteristic scale that characterizes that. Yes, okay, maybe HH a bad notation. Yes, of course, HH is 0. Yes. But, yeah, if I define T as the proper time, be of order that. Yeah, I should just put TH to 4. Stop doing this. Yeah. Although you're the first person that's upset. To be honest, it upset me when we and Emmanuel were writing it down, as I've forgotten that it upset me. Okay, so let me sort of start to just wrap up. Okay, so like I say, what are the observational consequences of this? Well, not much is annoying actually, because locally it's just GR with a small cosmological constant. Okay.
Sorry, because I'm not sure I answered the last one. So you're saying that this lambda effect, this small cosmological constant, is not going to be the observed one?
No.
Oh, no. It's going to be
Not dark
much
energy.
smaller than that.
Yes. So you need something to drive dark energy within this picture. Now, there is.
And we run into the usual then problems of the cosmological constant with this dark energy. I mean, if I take scalar fields with this dark energy, I still have to explain why this effect in cosmological constant.
Right. Yeah, sure. But you can, right? Absolutely. So, so you can take sort of well-behaved models of quintessence, and absolutely, you'd be crazy not to. So, for example, one thing we're looking at is like a linear potential which has a pseudo-symmetry. These sorts of games, and I think people now start to talk about inflation, which is they're really keen on talking about inflation that's natural. So, we've got natural inflation, we're going to have natural quintessence as well. So. Okay. So I'm stopping. Okay, so yeah, we haven't solved the whole cosmological constant problem, but we solved the standard model part of it.